Hello everyone, welcome back to my channel. I was requested to make a tutorial about QuantumVITAS. So in this video I will show you how to use QuantumVITAS. If you want to download QuantumVITAS, you could go to the official website quantumvitas.org and go to download page. If you use Windows, you could download this ready-to-use version. So it contains QuantumESPRESSO and Pseudopotential libraries as well as QuantumVITAS. And later afterwards, if you want to upgrade, for example, if there is a new version, you don't have to download this ready-to-use version because that is quite large, a few hundred megabytes, but you can just download the core program here. For Linux, there's no ready-to-use QuantumESPRESSO, so you could download this QuantumVITAS plus the Pseudopotential libraries. And as I said, if you later would like to upgrade QuantumVITAS, you could just download this core program, which is only a few megabytes. And then there's this quick start that describes how to use the program in Windows as well as Linux. In Linux it is a little bit more complicated because you need to use terminal, but in Windows it's very straightforward. Just double click .exe file and then that's it. So you could also go to Github to see the source code as well as the descriptions. You could go to the releases, and those are the release note that contains a description of all of the features. And you could also download the programs here, where this windows.zip is the ready-to-use version and .exe is the core program in Windows. .jar is the core program in Linux, and this is the version with QuantumVITAS plus the Pseudopotential library. Okay, so I have already downloaded the software, and then this is the ready-to-use Windows version, and I have already decompressed it. So this is what you should see. We can just run the program. The first time you run QuantumVITAS, it will show this message, welcome to QuantumVITAS, and it tries to make a new setting file. And then you see that the setting file is basically made in the root directory of QuantumVITAS. So before everything, I would like to show you the structure of QuantumVITAS. This is the main program that is located in the root directory, and then this is the executable for QuantumESPRESSO, and all of the programs that you need to use. For example, this pw.x is here, and then ph.x, that is for the phonon calculation. So everything is here, and in principle you could just use this and use command line to do calculation in Windows. That's the same. And then this is Pseudopotential library. QuantumVITAS comes with SSSP library and then Pseudo-Dojo library, and if you want, you can also download the basically here download the PS library, and then decompress, put the PS library folder here, and then the program will recognize the PS library as well. Okay, one thing to keep in mind is that you should not change the folder name of this one and this one, otherwise it will not recognize the Pseudopotential library. So now we open QuantumVITAS, and then the thing you notice is that everything is grayed out. The only button you can press is here, that you need to set the workspace folder. So this is the important thing. For example, we could just make a new folder here. So everything is located in the workspace folder, like all of your projects and all of your calculations. So you need to specify a workspace folder, and I recommend that you shouldn't put anything other than the input and output of QuantumVITAS into this folder. Just make a new folder and always keep it with that. Let's make it larger. This is the directory for QuantumESPRESSO, and it should recognize the default directory that comes with QuantumVITAS. You can right click here and open with external to open the directory in the System Explorer. You could also do it here, Okay, and then this is the directory for the Pseudopotential library. It should also be automatically recognized in the case of Windows. In the case of Linux, or if you just download a core program, maybe this would not be green but would be red. and in that case it means that the directory is wrong, and then you need to press here, we go to some other directory, and then press select folder, yeah. And then if it is green, then it means that this directory is okay. If it is red, you have to choose another one. And then here there's a toolbar. You can save the current project, and then to show the input file and run the calculation. And on the left hand side, this is a tree view of the project. So everything that exists in the workspace would be listed here, and all the calculations. Right now there's nothing, but later you will see that if you add a new project, there will be something there, yeah. On the right hand side, there's also nothing here, but later if we add calculations, there will be the input parameters here on the right hand side. So let's get started. Just a new project. For example, we want to calculate silicon. Okay, and you see that in the center, this is the workspace titled silicon. This is the name of the project, and you see that this now is with geometry. So we have to specify the geometry of silicon crystal. Let's say we want to use FCC lattice, and then around 5.4 angstrom. To define the atom silicon, you need to use the name of the element correctly, yeah. One is at 000, and after you input the XYZ coordinates, press here, add, and then 0.25, 0.25, 0.25, yeah. So this is the silicon crystal structure. You could go to the Cartesian coordinate and change it to the conventional cell, which is a very handy feature here. And you see that this is the familiar silicon crystal structure. For example, if you want to add another atom here, let's say 0.15, yeah, and then we could also fix some of the coordinates in the case of optimization. So we add it, and you see that for the fixed coordinates, they are labeled with a yellow background. To change that, you could select the entry and then do some changes and then press update, yeah, and then it will change. For example, if we want to change it to 0, and then we could update, and this changes to 0. If we want to delete this entry here, press delete button here, yeah? So select and then press delete button. We still need to have 0.25, 0.25, 0.25 here, and this is the unit. In this case, we use ALAT. That means everything is in the unit of this A parameter here. Okay, now in the elements, it should already be automatically chosen. So you could choose the pseudopotential library here, PS library or SSSP library, and then you could choose the functional and also the precision. For example, for the pseudo dojo, you could also choose whether this is relativistic or not. And for example, LDA, PBE. So this is very handy, yeah? You only have to choose which library to use and what kind of functional you want to use. Sometimes we will see that this part is red, and in that case it means that the system cannot find the requested pseudopotential, yeah? So either the pseudopotential library is not correctly pointed, or in some cases there are some elements that does not fulfill a certain criteria to use that here, yeah? Okay, so in this case you see that it's green, and the atomic mass is also automatically loaded, so everything is fine. Now the geometry has already been defined, and then we could add a calculation. So the most simple calculation would be a single energy calculation, that's self-consistency calculation. And then here you see that almost all of the input parameters are set to be default, which is very handy. So you only have to focus on the few that is left if you are not familiar with everything. For example, you need to choose the cutoff for the wave function here. For that, you could go to geometry. You need to press here on the left hand side and go to the geometry, and then you select the element here, and you see that there is a suggested cutoff of wave function and the cutoff of charge, and it's 30 to 140. So then we go to here, uncheck this, and then use 240 Rydberg. Now if you want to change something, you could uncheck that and then change that, yeah. If you want to set it back to default, you could just click on that. This will be grayed out. It means that it was set to the QuantumESPRESSO default. And then let's make the K points a little bit denser. So that's basically it. If you want to add magnetism or DFT plus U, you could check here. And then there are some options here. Yeah. In the case of silicon, we don't need that. So that's basically it. We could directly run the calculation, but we could also show the input first to check whether everything is correct. And if you scroll down to the bottom, if there is any error or warning, there will be some additional message at the bottom. Now it seems that everything is okay. We could just run the calculation. You will see this dialog here. Now it doesn't really make sense, but it is useful later. If you have multiple steps, you can choose which step to run. You don't have to always run everything. So we can start, and you see that it's running with this program, and it is SCF step, project, and calculation name. In the center, this is basically the input-output workspace. Refresh everything, and it will automatically go to the highlighted output file. And you see that this is the self-consistency, total energy versus the SCF iterations. It converges at the fourth iteration. In this case, there's not much else to see. You could also go to the raw text, and this is basically the output file. You can also go to the information summary, and it is summarize what are the important things in the file. Also, you could go to the plots. Yeah, press open with. It will open with your system's text editor. So this is a simple calculation. Now I would like to show you the second one is the optimization. Sure, we could optimize the silicon crystal constant. Yeah. One thing that you may notice is that if you add a new calculation, everything is lost. For example, previously we set cutoff of wave function to be 30 and then cutoff of charge to be 240, but now it does not change with it. To do that, we could go to the calculation that you already set, for example this SCF step, and press set as project default. Yeah, and then in the optimization calculation in the SCF step, you could sync from project default, and you see that now everything is automatically synced from the step that we want. Yeah. Okay, now we need to set some input parameters for the optimization. In this case, we want to relax the cell as well, and we uncheck the energy convergence threshold. We make it a little bit more stringent, and then let's see, let's -4, and then for everything else we kept it as default. Now we could also show the input file here, and there's no error in the end, so that's okay. So we could run the calculation. There's only one step. Like you see that this takes a little bit more time, but you could also already refresh here, and you see that there's this plot here. Yeah, but this calculation has not finished. So if you press refresh, it will refresh the plot here. And for the optimization, there are actually more options to plot it. You could plot the last self-consistency step. You could plot the optimization step here, and then you could plot the force convergence, and this is the pressure convergence. You see that pressure goes down and converges. And in the case of optimization, other than the raw text and information, you also have a choice to plot the 3D geometry here, and you can navigate. There are 5 steps here. So if you see carefully, the size of the cell changes. And then the question is, how can we update the geometry? To update the geometry, you could press here, Save Geo, and it says that successfully added second geometry. And then we could go to the geometry here. There's this use the following geometry. You could actually navigate the first, the original geometry, and then the second, that is the geometry that we used. Yeah. And the second geometry, that is the geometry that is relaxed. Then we could add a calculation, let's say the density of state calculation. To use the new geometry in the density of state calculation, you could use the second geometry. You could also use the original geometry. Yeah? And then SCF, you see that it has not taken the value that we wanted to use before. We could press sync again, and everything is updated. Now the non-self-consistency calculation, we need a little bit higher K-point density. And then for silicon, we could use tetrahedra method. And for the tensor state, we just plot all of the bands. Yeah. Okay. It's always a good idea to check the input before running the calculation. So now it seems that everything is okay. You see that now there are 3 steps. It shows first step. If you don't want to see the inputs afterwards, you could press here, yeah, and then it will not show it. If you want to see it, you could press OK, and then it will go to the second step, and it's fine, and OK, go to the third step. And then we could run the calculation here. You see that here it allows you to choose which step you want, yeah. But now, since we start from scratch, we need to run all of the steps. Now it's the NSCF step. And then this is the tensor state step, yeah. Okay, so now everything's finished. You see that this is the tensor state of silicon with the Fermi energy in the gap. And here you could choose whether it's the tensor state or integrated tensor state, yeah. And also there's an option to show the marker. Then you actually see what are the data points. To save the project, you could press here, save current project, and then it will save everything, including the geometry, self-consistency calculation, optimization calculation, and the tensor state calculation. To navigate through different calculations, just click on the tree view on the left hand side, and for the geometry you need to go back. Yeah. One thing to notice is that although you see there's a geometry tab here, you cannot change the geometry here. If you want to modify the geometry, you have to go to the geometry here, yeah. Okay, so this is the tensor state calculation. We could also do an electronic bands calculation. As usual, we sync from the project default, and then for the bands, actually here we use crystal. So this is a bug here. The label of this button is not visible. In principle, this should show add. For example, let's say this is a gamma point. You don't need to have this label here, but yeah, I just implemented here. Is 0, 0, 0, and how many points? Let's say 20 points. And then you need to add, press this button on the right hand side to add it down there, yeah. For example, you have multiple points, and if you want to change something, for example, if you want to change to X, you just select the item from the table, and then, for example, 0.1, yeah, and then press update. You could also delete the item. I would like to show you something that is quite cool, is that you can paste from external, from the QuantumESPRESSO input file. I would copy something from my GitHub. So here you could find actually many QuantumESPRESSO input files. For example, the silicon bands calculation, that's basically here. Go to here. In principle, you only need to copy it starting with K points. That is important. You could also copy the whole input file, it's not a problem. So paste from external. If you are not sure whether this will work, you could go to preview, and it says that okay, everything is red, and then we save. So that's it. And then we could actually run the calculation. This time we don't check the input here, we just run the calculation. And first it's the SCF step and then the bands step. We could refresh. Basically those things shown here are the files that are in the calculation folder. And you see that this is the silicon band structure, very easy, right? This is the Fermi energy and all of the bands. You see that this is a semiconductor. Okay, to give you an idea how the project and the calculations are arranged, let me just show you. You could press here, show in the system, and then it will open the calculation folder. You see that in the workspace folder, there are this silicon folder, that is the project folder, and then under the project folder, there are multiple calculation folders. Yeah, you see every calculation corresponds to one calculation folder. And then in the bands calculation, everything you see here are actually just files that you see in the folder. Okay, we're just gonna close that. And then you could also delete things, but maybe you should be careful about deleting things because maybe something depends on others here. Yeah? But if you want to delete that, you could press here, delete. Yeah. And the good thing is that now you could actually do multiple calculations. For example, we want to do a second tensor state calculation, you could actually do that, and you see that the name is different here, and this is in a separate folder. You could use different settings. For example, let's say we would like to use a smearing occupations, and then do the tensor state calculation again. Now everything is independent, So this is finished, and you see that this is the smearing algorithm, but we could go to the tetrahedral, and it's better for this kind of semiconductor tensor state. We could add another calculation. I would not do molecular dynamics with silicon. TDDFT, okay, maybe also not silicon, So that's enough for silicon. We can save the current project, and then we could actually open a new project that is water. For water molecule, I will not construct the geometry by hand now. I will just go to my GitHub and copy the input file of water on here, basically in the input file, and we could copy the whole input file and paste from external input. You could preview and see that it recognizes everything and save. Okay, so you see that it is now 180 degrees, which is not true. So this is before relaxation. What we could do is that we could do a relaxation calculation, optimization, right? And basically everything else we kept the same, except that here this is a molecule in the box. We could use gamma point calculation, and for the optimization only ions, that is enough. Maybe for the energy convergence we use a little bit more stringent criteria as we used before. Okay, and now we could run a calculation and refresh, and then refresh here, it gives you the updated plot. Could also see the force here. Now it's finished. The problem is that here the optimization is not finished. So what we need to do is that we need to increase the maximum steps and then redo the calculation, and then let's see. So the energy converges quite quickly, but the force is a little bit more difficult to converge, and let's just wait a little bit. Now it's finished. You see that the number of total steps is 70, which is smaller than 100, so this is finished. To make sure, we could go to the information here and see that it tells you the optimization is finished. And then we could see the 3D geometry. Now this is the optimized geometry. And then could save the geometry here to the second geometry, and then we use the optimized geometry. Okay. Now we could do some molecular dynamics with water molecule. As I said before, although both calculations have SCF step, the SCF step is basically independent of each other. What you could do is to set one SCF step as project default, and then here we sync from project default. So the settings can be transferred to the new calculation. Now, so this is without thermostat. I could show you that run the calculation, refresh. This is basically an output file, and this is the plot of the kinetic energy. Let's plot the temperature versus time in picosecond, and you see the temperature oscillates around 3 Kelvin here. Now we could try to add some thermostat here. Let's see, maybe Anderson thermostat, and try to stabilize that around 300 Kelvin, maybe a little bit more, 500 Kelvin. And then we do the calculation again. Could refresh. Okay, change the temperature and trace the temperature versus time. See that temperature is much higher now because we turn on the thermostat, so it tries to stabilize at around 500 Kelvin. But of course this is a very small system, so the temperature will oscillate a lot. And refresh. When you see idle here, it means that all of the jobs have been finished. Now, the only thing left is the TDDFT calculation, which I will not do with water molecule, but we can first save the project. And to close the project, we could press this cross here, and then it closes. Press here, this closes. The calculations under the project will not be shown here. If you want to open the project, select the project you want to open, and then open selected. And then the calculations will be loaded. Yeah, we close the project. And then last project that I would like to show you is benzene molecule. For benzene molecule, I also don't want to input everything because there are a lot of atoms. Rather, I would also paste from external, go to the GitHub page in the QuantumESPRESSO tutorial, benzene TDDFT. Yeah. So benzene SCF, we could copy everything and here paste external. So in the input file, save, and you see that this is the benzene molecule. Yeah, we could increase the bond length a little bit to connect everything, and basically that's it. So for the calculation, the TDDFT calculation, for TDDFT it's very important to use gamma point in the K point, and the occupation should be fixed. Yeah, so you shouldn't change that. And then the polarizability, we choose 4, and all iterations, like we need to use this extrapolation, and let's say maybe make it a little bit quicker, so 4000. And then OSC extrapolation, we use electron volt here, and then from 0 to 50 electron volt energy step would be 0.01. Now we could run the calculation. Start. This will take a while. So in this case, if you refresh and you see that there is a crash here, it means that there's something wrong with it. The error message is quite easy to understand. It means that it is not implemented for PAW pseudopotential. So one thing for TDDFT is that you cannot use PAW. How can we change the pseudopotential? We need to go to the geometry page. In the elements, there are pseudopotentials. How do you know it's PAW or not? You could select here and you see that this is PAW. So carbon is PAW, but hydrogen is US ultra soft. For SSSP library, you cannot really choose PAW or ultra soft. One element has only one pseudopotential file. So in this case, we need to use pseudo-dojo, which is norm-conserving pseudopotential, and this should be fine. And then we do the TDDFT again. So run and start. Maybe this has taken too long. If you want to stop the job, you could press job control, stop current job, but in this case it will still run the next step. So if you are running multiple steps and you want to stop everything, you could stop all jobs. So here, stop all jobs, and you see that now all jobs are stopped. Now that we have stopped everything, if we want to start again, we could run the calculation, but we know that the first step is already finished. We could uncheck it and then run from the second step here. Okay, and then we just wait a little bit. Okay, so now it's done. It automatically loads the optical spectrum that is calculated from TDDFT calculation. The x-axis is h bar omega, and y-axis is the oscillator strength. And then we could save the current project, close it. The next time you open QuantumVITAS, you will see everything in your workspace. If you want to open something, you could open selected, and then this is the TDDFT calculation that we have just done. Okay, so basically that's it for the main functionalities of QuantumVITAS. If there's something that is not clear, please leave a comment below, and I will explain to you how to do that in QuantumVITAS. I have shown you the usage of QuantumVITAS in Windows. Now I would like to briefly show you the usage in Ubuntu, basically Linux system. The download page for the Linux version of QuantumVITAS is basically the same. I would recommend you to download this pseudopotential libraries included version, and I have already done that. It's basically here. I can list the files inside the folder, and you see that this is the Pseudopotential library and this is the QuantumVITAS core program.jar. Yeah, in Linux it is a little bit more difficult than Windows, but it should be fine. You could go to the quick start in the official website and scroll down to the Linux, and basically it tells you how to run QuantumVITAS on Linux. The first thing that you need to do is to download the Java runtime environment 1.8. Sometimes your Linux distribution comes with Java, but usually the Java is the open source version and it does not work. So you need to download this version here. That is the Oracle Java, and basically Java download. And do not download Linux RPM, but Linux x64, yeah, this one. So just press here, save file, and in the download we could open the file. You see there is a folder with everything inside. I have already downloaded that here, and you should decompress it somewhere, for example here. You don't need to install anything, you just put the folder anywhere that you want. Basically the only thing is that in the bin folder there is Java program here. Okay, so let's go back to the quick start. So you could add a Java home and then export the directory to the path. I will not do it here, but just add that to the end of the bashrc file and then restart the terminal again. Now if you type in the command java -version, it will give you the Java version. Okay, so go to the QuantumVITAS directory and use this command here. So the Java should be lowercase, not uppercase. Okay, now it tells you that there's no setting file. This is usual for the first time. And just set a workspace here. For example, we could go to the workspace that we just used for the demonstration of Windows calculation and then open that, and you will see that it also reads that part. Yeah, you can open selected project and you see that it's plotted, so everything is cross-platform compatible with different platforms. That is good. One thing that you notice is that the Pseudopotential library is automatically loaded, but the QuantumESPRESSO is not, because in the Linux right now there is no ready-to-use QuantumESPRESSO version. We need to select the directory that contains QuantumESPRESSO. If you don't know how to compile QuantumESPRESSO or how to install QuantumESPRESSO, you could refer to my previous videos about how to do that on Linux. Yeah. And I have tested version 6.1 to 6.5, and you are welcome to test other versions as well. So open, and you see that this turns green, which means that everything is fine. Okay, now we could make a new project here. I would like to show you the spin polarized calculation for iron. We first set the geometry, that is the BCC lattice with 5.096 Bohr, and then the atom, we only need one atom here, 0, 0, 0, add. We could change to Cartesian coordinate to make it in the conventional cell and see that's a BCC lattice. That is good. And then it is automatically loaded this pseudopotential file. Yeah. Okay. Then we would like to do a dense state calculation, and in this case we can turn on the magnetism, choose spin polarized calculation, collinear calculation, and we set the magnetization to be, let's say, we give the iron atom a little bit kickstart. You cannot set it to be 0, but you need to set it to be something larger than 0, otherwise it will stay at 0. So the way to do it is to first select and then change the magnetization and then press update. Now it's updated, and then for the standard settings, maybe we want to choose a little bit higher point density here. That's a 666. And the smearing we use in this MV smearing, or 0.005, let's say. And in the non-self-consistency step, we use tensor K points. We change the smearing again, 0.5. And in dense state calculation, we calculate the whole energy range. Let's see what's happening here. And then we could start the calculation now. Okay. now everything is finished. You see that there are some low-lying levels that is quite localized, and actually we only need the energy range between, let's say, 10 to 35 electron volt. What we can do is that we could go to the density of state step, and from 10 to 35 electron volt. Okay, and then we do the calculation again. Now we don't need to do the first 2 steps, we only do the last step, and we start. Yeah, okay, now it's finished. We could refresh the plot here, and now you see that the spin up and spin down is splitted, is shifted, so that we have successfully calculated the magnetism of iron crystal. So basically that's it. Today I've shown you how to use QuantumVITAS in Windows as well as on Linux. QuantumVITAS is cross-platform, everything is exchangeable in different systems. Just as a side note, this is a temporary tutorial. In the next versions, probably some features will change, but the main structure would remain the same. So if you learn something from my video, I appreciate your like or subscribe to my channel, and I hope to see you next time.